Hey there, my name is Brennan, and this is Lab 3 for Black Hole and Orbits. The purpose of this lab is to better understand curving motion using coding setups for orbital mechanics. In this case, specifically, finding the mass of a black hole based off of the force data of a star that's orbiting it, and then trying to get a rocket ship into a stable orbit in a planet and moon system. So the models that we're using here are all similar to ones that we've been using before. Same as in the first two labs, we have the velocity update formula, position update formula, and we're using a lot of Newton's second law, F net equals derivative of momentum, excuse me, derivative of momentum taken in respect to time. We also have to use universal gravitation for this one, and since it's curving motion, we have F net parallel and perpendicular. Specifically, we're using parallel where it's magnitude of final momentum minus magnitude of initial momentum over delta t times p hat. So for part one, we just have the mass of our star, delta t as 1 day, magnitude is equal to mass, momentum is equal to mass times velocity, change in momentum is final minus initial, and then the derivative of that in respect to time we can approximate simply as change in momentum over change in time, which, as we know with Newton's second law, is numerically equivalent to F net. So the specific parallel component, like we said, is going to be that magnitude, change in magnitude over change in time times p hat. And then to find the perpendicular component, we can simply solve by subtracting the parallel from our overall net force and algebraically rearranging our universal gravitation formula to solve for the black hole gives us this, and from there it averages out data-wise to about, I got 1.35 times 10 to the 34th kilograms as the mass of my black hole. The initial conditions for this are just these two positions between the star and black hole, and the star has its own initial trajectory. With our system, the star with the black hole and the surroundings acting on it. Part two is with orbits, is really just a whole lot more application of that universal gravitation. So we have the position vector between any two given things is just the second minus the first, where the gravitation is equal to g times the two masses times r hat divided by the magnitude of r squared, where the force on any given object is just the sum of all of the individual forces. Yeah, we use the velocity update and position update, of course, and throwing all that together, I was able to, after a little bit of trial and error, get an initial velocity of this to get this nice little trefoil orbit. In this case, our system varied depending on what we were calculating as the F net on each given thing, but our ship was our system when we were concerned with its velocity. And our initial conditions were simply with the rocket on the surface of the moon orbiting the planet and about to blast off. So as far as discussion, while net force and rate of change in momentum are numerically identical, they actually do mean different things here, where F net is the actual force is the work being done on the system, while the rate of changes of momentum is something that is just observed in the movement of the system. If our system in part two had been fully populated also with the star and black hole, obviously everything's gravitational force on everything else would have to be calculated separately and added together, and it would get a whole lot more complicated. Although it is important to note that obviously the black hole would have a whole lot more of an impact on everything than pretty much anything else in that system. And that's all for this week. Bye.